Let's look at another effect of light motion in the presence of a gravitational field, in particular gravitational field of spherical massive object, which is the gravitational retardation of light, or superior delay. Now, as I mentioned, reflection from light of light from the sun is thought to detect and only possible during a total solar eclipse, when the eclipse blocks out the optical wavelength from the sun. And gravitational retardation or time delay of light is another effect. So let's ask, what is gravitational retardation or time delay of light? So it takes more time for light to travel from the source to the observer in the gravitational field of a massive object than in flat space due to the deviation or deflection of light rays. And as a result, there is a delay in reception of the signal. So let me consider there is a source, there is an observer, and when no massive object is around, the trajectory will be a straight line, and this would be the path of the light ray, and we can record the time. Now let's say all of a sudden we have a massive object in the vicinity. Then what would happen is that if I shoot light ray in the direction of the observer, this will get pulled away towards the gravitational object, so this will not reach the object at all. So instead, one needs to light has to travel in a path from the source to the observer using this curved path in this curved geometry. Remember, now the geometry is curved. So clearly the distance is longer than the usual flat distance in flat geometry. As a result, the time to receive the signal from the source would increase because your light is traveling a longer distance. It will take a longer time. So if you measure these two different, the time of flight of light in these two different cases, when there is a mass in the vicinity, when it's away from the vicinity, you should be able to record a different time, in fact a delay in the time. Okay? So this is what is in a nutshell superior delay or gravitational time delay. And this is much more convenient to measure and much more accurate to record, because instead of deflection angles, which are very small, as I mentioned, these angles are very small, so it's very difficult to measure. Time delay, on the other hand, we have very accurate clocks which can measure up to billionth of a second, so we already have very accurate atomic clocks, and time measurements are much more easier than angle measurements. And as I also mentioned, that these entire experiments can be done with non-optical light, that is in fact with radio waves. So we don't even have to wait around for an eclipse for this gravitational retardation of time delay. So the fact that this happens, or this was acknowledged by President Shapiro in 1964 and was verified by his group at the MIT Lab conducted a couple of years later, 1967. And then they bounced radar beams of Venus and Mercury at the American reference, I will explain in a second. And they noticed recording the time, and of course they found it to be more than what it should be. It had the sun not being in the picture at all. So this is not a very good picture. The idea is, let me just draw a second one. This is Earth. We can draw regarding the point object, and then let me draw Sun, which is this. So normally, we will be able to see objects which lie in this. We draw a couple of tangents, and normally anything outside so this is in the shadow. This is any object which is in this shadow region. We will not be able to receive light from that. Okay? We will not be able to see it, even during we will not be able to see it because they are being blocked by the sun. Now it so happens. So let me draw this thing. This is the center of the sun, which is the center of our coordinate system. And let me this distance is the solar radius, 0, and of course this is the distance from this r, which is the distance from Earth to the center of the Sun. Okay. Now, as I said, that within these dotted lines, any object here will be blocked out of view of Earth because they're being blocked by the Sun. However, due to gravitational deflection of light, even when, let's say, the planet Mercury, which is here, very close to the Sun, even when Mercury slips into the shadow region, because of deflection of light, we will be able to see Mercury. Okay, so because this is, instead of taking this route, light from behind, which is called superior conjunction, will be able to be sent to Earth. Light from Mercury will reach us because it takes a curved path. Okay, this is curved because of it would have escaped. At Earth, we won't be able to see this light. Sorry about that. But because light is being pulled towards the Sun, it gets bent and it eventually reaches Earth, and we're able to see the planet Mercury at the superior conjunction. This is what I've drawn here. So this blue dotted line would have been the tangent. This is the tangent. The blue dotted line, which is the hypothetical line, has the geometry being completely flat, and light travels in a straight line. Instead, in the effect of the Sun, we have the Schwarzschild geometry or the Schwarzschild metric, which is curve metric, and the light ray would take this red dotted line. Okay. So superior conjunction is when it goes into the shadow region, just into the shadow region. Okay, for working out the theory or theoretical expressions, we need to start with, again, the light ray using the constraint convention. So this is light ray constraint. And then, because we want to determine t as a function of r, I'm going to divide c out by dv lambda squared, this. And then I'm going to use the integrals of motion to substitute some of these quantities, replace some of these quantities, which I've done here. And then this equation will lead to a first order ordinary differential equation. R is a function of t, or t is a function of r. And we can write down a solution. But before that, as before, what we have done is I've replaced the L, the conserved charge L, with the point of nearest approach, or the periapsis, R0, the radial coordinate of the point of nearest approach, or the periapsis point. And I've replaced it here. And you can see instead of R squared, we have R squared times this quantity. And this is the first order ordinary differential equation. We can write down a formal solution, which I've written down. Now, I've brought back a factor of 1 over c, because I want to look at an answer in SI units instead of natural units. Because at the end of the day, I'm going to plug some number and compare with data. So the closed form solution has an extra factor of 1 over c compared to what we saw in the last slide. And as before, for weak gravitational fields, we can process this derivatively by expanding the powers of g and m over r times c squared, or g and m divided by r naught times c squared. Now this expanding the denominator and the numerator is left as a homework exercise. The leading order solution, that is first power, is given by this. Will be the zeroth order solution. Remember, zeroth order solution would be, when we go back to the diagram, is this blue line. And using Pythagoras theorem, you can tell that the time taken would be to this blue line using Pythagoras theorem. This is the right triangle. So r0 squared minus r0 squared, r squared minus r0 squared will give you the length of this blue path, blue dotted line, and divided by c will give you the time, usual time. So this is in the absence of any gravitational deflection, and this extra part, which is proportional to g and m over c cubed, is due to the deflection of the path due to light. Okay, so this I will call the delay delta t to the right, and the equation of power. or the Shapiro time delay. Okay, this is called the Shapiro time. Okay. Now, one pedantic thing. Remember, t is actually time recorded by clocks at spatial infinity, not at arbitrary radial location r. Remember, this t coordinate, the Schwarzschild time, is actually the time which is being recorded by clocks at infinity, spatial infinity. So, if you are interested in the clocks at finite radial location, let's say at some radial location r, those clocks, because they're inside the gravitational field of the sun, they will tick slower due to gravitational time dilation, an effect which we discussed earlier in previous lectures. So this time delay located at the radial location r, which I'm denoting by delta tau times r, will be obtained by starting with the time delay for the Schwarzschild time multiplied by the appropriate gravitational time dilation factor, okay, a redshift factor, which is square root of minus g00. Okay, if you do that, then compared to this Schwarzschild time delay, you'll have an extra term because now the delay will become smaller because we are on clock are ticking slower, so the delay will get reduced by this one minus r square over r. So this is the but what I've seen in literature by Shapiro time delay, people usually refer to the delay in the Schwarzschild time, not in proper time, in proper radial time. Okay. Now for a round trip, let me go back to the figure which I have drawn. This figure, let's consider radio waves being bounced from Earth off Mercury and back to Earth. Okay, so the time recorded will be twice what we calculated, and hence the delay will be twice what we have computed. Round trip time delay will be twice of this, or if you're interested in the Schwarzschild expression, it will be twice of this. And this turns out to be, this round trip time delay turns out to be of the order of 100 microseconds for Mercury and Venus at their respective superior conjunction. And that could be recorded with existing radar technology in 1966-67. Remember, at that time we did have radar technology and we could measure 100 microsecond accuracy was within the accuracy of the clocks at that time. So this could be measured easily in 66-67. And the measurement of the time delay from the radar bounced off of Mercury and Venus is found with this the fourth one of the classic tests for Mercury. And it was the last one which was done in 67. The first one was 2019, what we learned today, Gravitational Deflection, and the last one in 66-67, which is Shapiro time delay. We will conclude our lecture here. Let's look at the summary and provide an outlook for our lecture. So, first thing we did is to examine light-like geodesics in the Schwarzschild geometry. We wrote down the geodesic equation and the light-like constraint of the geodesic, and we also wrote down the inequals of motion. We saw that motion is confined to a plane, just like in the case for time-like geodesics, and that there exists inequals of motion. Now, unlike in the case of time-like geodesics, we cannot interpret these integrals as specific angular momentum and specific energy. And in fact, one of them was scaled to 1. And then we solved the radial equation using the first integral and light-like condition. We solved for the orbit first, and then for r as a function of t, or t as a function of r. And each of them gives two important effects. Solving for the orbit, that is r as a function of phi, or phi as a function of r, led us to the important effect that light is deflected by gravitational fields, in fact, it is attracted towards gravitational fields, and we computed the amount of deflection of light, gravitational deflection of light, And we also worked out the second important physical effect, which is Shapiro time delay, or gravitational retardation of light, in which light seems to take more time to come from a given source to an observer in the presence of a gravitational field. And we worked out this expression as well. I'll leave it as a homework to work out this time delay. I've been very schematic. So you can plug in the numbers for when mercury is at superior conversion and work out how much this amount is. So next lecture we will start to apply general relativity to understand the large scale structure of the universe, cosmology. In particular, we will look at spatially homogeneous and isotropic solutions of isothermal liquid with matter. So we will look at non-vacuum solutions. So far we've been studying vacuum solutions. We will study non-vacuum solutions, and unlike spherical symmetric, these will be homogeneous, but all points look the same. So these will give rise to this FLR of the universe. Okay. All right, I'll stop here. Thank you very much for your attention, and I will see you next time.